So we are moving on to the second part of 1.1. So if I had a graph of your speed, so let's say that you're driving to Price and you start off really slow and you speed up and you speed up and you speed up until at some point you reach your maximum speed and you go that speed for a while, and then when you get to Price you slow down. So that graph might look something like this. You're speeding up, and then you hit the highway, then you have to slow down a little bit through Huntington, and then you speed up again, and then you get to Price and you stop. So this would be time, and this would be speed. Okay. When were you speeding up the fastest? Well, first let's highlight, when were we speeding up? All of this I'm speeding up. And right here I'm speeding up. When are we slowing down? So this would be a slowdown time, and this would be a slowdown time. And what are those times? Constant speed. You set your cruise at 65 or whatever you decide to go at. Okay? So when are we speeding up the fastest? How would we tell? It will be by the rate of change. Good job. If you don't know, he looked at the problem and just read it off. He has no idea what it means. Oh, good. It's the slope. So in those sections where I'm speeding up, the steepest point would be my fastest acceleration. So here I'm speeding up kind of slowly. And then somewhere in here I'm speeding up the fastest that I sped up, right? At that moment you are pushed back into the seat harder than you are at any other time. Okay? So how do we figure out how fast we're speeding up? Well, you can find what's called the average rate of change. So from here to here, if we drew a line, that would tell me my average acceleration. What if I wanted the acceleration of this point right here? Well, what you would do is move these points closer and draw a line, and move them closer and draw a line, and move them closer and draw a line. And you can see that line is sort of getting steeper. And eventually, when I move those 2 points really, really, really close together, I get a line that will tell me how fast I was accelerating. Okay? Now, in calculus, you can actually find the acceleration of a single point, which is not something you know how to do here, because the slope of the line is y2 minus y1 over x2 minus x1. Well, what happens when I bring those 2 points together? My x1 and my x2 are the same number, and my y2 and my y1 are the same number. So you basically do 0 divided by 0, and the equation breaks. But there is a way in calculus to find it. So if we were to look at the position graph, so this is a graph of time and distance, how far we've traveled. Okay, so let's say we do this. Oops. No, that's boring. Let me do a better job. Okay. What is happening right here? Constant, meaning, so if you're driving in your car, no change, meaning you stopped, right? This is time versus distance. So when the graph is flat, this tells me I'm stopped. Okay, let me draw a better line here. There we go. Okay. What's happening? Sorry, guys, I'm not very good at drawing. What's happening here? I'm moving forward. What else? So I'm moving forward, but it's a straight line at a constant speed. So during that interval, I guess this interval, I'm traveling at a constant speed. I've set my cruise control. So what's happening here? You're accelerating. Okay. All right. What's happening here? Decelerating. It's not constant. It's not a constant slope. And then I stop. And what happens there? Accelerating. And then here, decelerating. And then here, I'm stopped. What if it went like this? You would have turned around and come back, right? I would have hit reverse and gone in the other direction. So calculus allows you to look through this and figure out exactly what's going on. The best we can do is give sort of a summary of what happened between 2 points. So if I wanted to know how fast was I traveling in this interval, I can't really tell, but I can find the average speed. So if I put a point here and a point here, and I join them with a line, and I find the slope of that line, it will tell me my average speed. However, for a little while, let's say that that's 65 miles an hour, for a little while I was going slower than 65 miles an hour, right? And then for part of it, I was going faster than 65 miles an hour. But when it averages out, that will be 65 miles an hour. So this is called the average rate of change. So in this class, there's no way to look at the graph and figure out exactly how fast you are going at any moment. But I can find your average speed between 2 moments. And then next year, if you take calculus, you will find out how to find the instantaneous rate of speed. So basically, your speedometer lets you know how fast you're going right now. There is a way to figure that out using a graph, using calculus. But the formulas we have don't work, because if this is my curve and those are my points, the average rate of speed is equal to the slope between those points, right? Well, what if I want this point here? I can move these closer and closer, but when they occupy a single point, my slope formula is y2 minus y1 over x2 minus x1. And what happens when these 2 points touch? y2 and y1 are the same number. And then we get 0 divided by 0, and the equation breaks. Okay. Calculus allows you to divide by 0. It also allows you to divide by infinity, or multiply by infinity. Or you can do 0 divided by 0, or infinity divided by infinity. What is infinity divided by infinity? It depends. What is anything divided by itself? 1. Okay. What happens? So x over x equals 1, right? But what is infinity divided by any number? Infinity. And what is any number divided by infinity? So let's say you have a 7-foot stick, and I tell you cut it into an infinite number of pieces. How big is each piece? Well, you just keep cutting, and then I come by and I measure one, and I say, wait a minute, you're not finished. Keep chopping. And you keep chopping. I come back later, and I measure a piece, and it's really, really, really small, but you're not done yet. So you keep chopping. Where are you headed? Every piece is length 0. Right? You take a 7-foot stick, you cut it into an infinite number of pieces. How long would each piece be? So tiny you couldn't even see it. In fact, if you can measure it, then you didn't chop it enough, right? Which means you'll never be done. So what is infinity over infinity? Well, it depends. Sometimes it's 1. If the two infinities are the same size, then the answer is 1. But sometimes the top infinity is bigger than the bottom infinity, and the answer is infinity. And sometimes the bottom infinity is bigger than the top infinity, and the answer is 0. How do you know? Well, you need calculus to figure that out. Oh, calculus is the most wonderful math class ever. So I took calculus as a senior, and I got in there, and it was the first time in my life that it all made sense. All the things you've ever learned, they all are built aimed at calculus, and calculus is where everything comes together. So here's a problem. What is 0 divided by 0? Well, 0 divided by anything is 0, and anything divided by 0 is undefined, and that's the wimpy middle school teacher's way of saying we're too lazy to tell you that the answer is infinity. So if you have a stick and you cut it so that every single piece has length 0, how many cuts did you have to make? An infinite number. So sometimes 0 over 0 is 1, and sometimes it's infinity, and sometimes it's 0. Sometimes. Now, this is really going to hurt your head. It all depends on how big your 0 is. So that one's a little harder to understand. The infinity one you can kind of agree with, but 0 is always 0, right? Well, imagine. No, it is 0. It's not something other than 0, but let's imagine that everybody had, let's say that 3 of you went out in the desert and picked these big rocks, and the rocks all weighed the same. And every year, some of the rock gets weathered, either through wind or water or traffic or something like that, right? Well, what if your rock loses its weight really fast? Then the graph of the weight of your rock might look like this, right? Eventually, how much is your rock going to weigh? Nothing. Eventually, it's going to blow away, right? The last piece of sand on the rock is just going to weather and blow away. So eventually, it will be nothing. Now, we can pretend that it's always going to get smaller and smaller and smaller, but eventually, when you get down to 1 atom, it's going to blow away. So this graph is approaching 0. Well, what if somebody else picks a rock of the same size, but it's sheltered a little bit, and it doesn't shrink as fast? Okay. Eventually, both rocks will weigh nothing, right? But one rock is approaching 0 closer than another rock. So if we divided these two equations, this 0 is smaller at any moment than this 0. They're all headed to 0, right? So in the long run, the answer to both values is 0. But one of them is getting there faster than the other. And so if you divide one equation by the other equation, sometimes if the rocks are shrinking at the same rate, then the division is 1. If this rock is shrinking faster than this rock, then the answer is 0. But if you flip it the other way around, then the answer is approaching infinity. So we're not actually dividing 0 by 0. We're dividing equations that are getting close to 0 by other equations that are getting really close to 0. And in the long run, they're both 0, but one of them just gets there faster than the other. And you can do the same thing with infinity. So if you have bacteria in a petri dish that are growing, and one of them's growing like this, and one of them's growing like this, you're going to have an infinite number of bacteria eventually, but one of them is growing faster than the other. So one infinity is larger than the other infinity. They're both infinity, but one just gets there faster. Gets where? To that number that you can't draw on the number line. Right? Where is infinity on the number line? Right? If I go out and I say infinity is right there, am I correct? No, because there's a number bigger than it. So infinity is larger than any number you can ever think of. But some infinities are bigger than other infinities. Yeah. I love calculus. All right. So that was a really long explanation for how we're going to do this. So this says find the average rate of change from height 0 to 2.2. So there's some graph like this where we shoot a rocket up in the air, and as time passes it goes down. We want to know what is the speed of the rocket on average from here to here. So this point is 0, 0, and this point is 2.2, 110. We just do the slope formula. y2 minus y1 over x2 minus x1. In this case, it's easy. 110 minus 0 over 2.2 minus 0. What if I get these mixed up? Is that going to create problems? As long as if you do the top backwards, you can do the bottom backwards, and the negatives will cancel each other, and it'll work out. What if I put the x on top and the y on bottom? That's going to mess it up. So it's got to be y on top and x on bottom. Rise over run. You have to rise up the mountain before you can snowboard down the run. Okay? Then you're going to find the same thing from 6.6 to 13.2. Question number 2. Finding the domain and the range of a parabola. Domain is the x values. So I essentially draw a vertical line, and I ask, when does this vertical line, sorry, wrong button. When does this vertical line touch the graph? Well, obviously it touches right there. So x equals 5 exists on the graph. What about over here? Is there a graph there? Yeah, there's going to be, right? I can't see it, but I could calculate it. If I knew the equation, all I would have to do is plug in -7 into the equation, and it's going to be really, really low. But there is a graph there. So is there any place I can put this line and miss the graph? Oh, but we're talking about domain. We're looking at the x values. So domain is everything. So the domain here is all real numbers. Okay. Well, let's look at the range. For the range, we draw a horizontal line. Is there anywhere I can draw a line and miss the graph? Yeah. Anything above 3. Oh, I did it again. So anything up here, there is no graph. Okay? So we could sort of say that the domain is all real numbers. That's the symbol for real numbers. And the range would be y is less than 3. Is it equal to 3? Is there a graph at 3? Yes. The only time there won't be a graph is if they tell you there's not a graph, if they put an open circle. Okay? So if you're wondering, does it hit 3? The answer is yes. The only time it wouldn't is if they specifically tell you that it doesn't. Okay? So we are going to label these as all real numbers and y is less than 3. You also need to know something called interval notation. So interval notation is like y equals small, comma, big. And you either use parentheses or brackets. Have you guys ever seen this? Okay. Parentheses mean not equal to, and brackets mean equal to. Okay. So if I said P equals 2 comma 3, that is the point 2 comma 3, right? If I said Y equals bracket 2 comma 3, that means every Y value from 2 with a closed parenthesis up to 3 with an open, that's an interval. It's like a number line. Okay. Now it's not going to ask you that here, but I think on the next one it does. Oh no, this is an average rate of change. So I want to know what is the average rate of change from 3 something to 6 something. How do I find the Y values? Plug them into the equation. Let's say I get 10 and 5. What should I do now? Slope. So 5 minus 10 divided by 6 minus 3. And that will find the average rate of change between those 2 points. Okay. So we have a graph 75 plus 15x squared. I'm going to rewrite this as y equals 15x squared plus 0x plus 75. What's the formula for the vertex? Negative b. So the x value is negative b over 2a. In this case, b is 0. So that wipes out the whole equation. So I know that my vertex is at 0 comma something. How do I figure out where that something is? Plug it in, and I get 75. Okay, so 0, 75. So on this graph, we want to go over 1, up 15. Everybody agree? So I don't have that point on the graph, so I would need to use this and say 1 comma 90. And then I usually go over 1, up 1, and then over 2, up. Normally, what would I do? Over 2, up 4. But this time I have to do over 2, up 4 times 15, which would be 60. So 2 and 60 higher than 75 would be 135. And then you do the same thing on the other side. And you will graph the parabola. Is that all it's asking? Let's look. Okay. So once you have the graph, write an inequality for all values of y given by the model over 5 minutes. So we draw this graph, which kind of looks like, it's going to kind of look like this. Okay, and it wants to know what are the y values from here over. So we need to plug in 5. When x equals 5, we stick that in there. And I get 15 times 5 squared plus 75, and I get 450. Okay, so what is the y going to look like after x equals 5? Y will be greater than or equal to 450 because the graph is going up. So from here over, the y value is going to be from 450 and up. that make sense? Okay. So here you have a parabola that is graphed and a quadratic formula. You have to find the vertex for function 1. Just use your negative b over 2a formula and then plug that number in to find y. Vertex of function 2. Which one has a smaller minimum? When we say minimum, are we talking x or y? Y values. So you're going to compare the y values. Okay. Is this parabola going to have a maximum or a minimum? It's going to have a max. How come? It's upside down. How do we find the max? We do negative b over 2a, and that is my x. And then I take the x and plug it in to find the y, and that would be the maximum. All right. Okay, here we have an equation. It costs a certain number of dollars to make an X-ray machine. So what's happening here is if you only build one X-ray machine, it's going to take a lot of time and resources to do that. You have to set everything up, you have to buy the building and all of that. So if you only build one, that X-ray machine is going to be very, very expensive, right? So that might cost this much to build. But what if you built two? The cost is going to go way down because you've already paid for the building and the workers and the tools and the materials. All you have to do is just buy, I guess not all the materials, buy a little bit more materials and pay a little bit extra to have somebody build it, right? So the cost of every single X-ray machine goes down the more you make. But there's usually a point where building more X-ray machines costs more money. Maybe you run out of room in the building, or maybe there's only so much material out there. And once you use up all the cheap material, then you have to buy expensive material from somebody else. So the cost per X-ray machine might look like this. Your first X-ray machine is really expensive. The second, third, fourth, fifth, they all get cheaper. But there is a point at which if you continue to build more and more, they get more and more expensive. So using this formula, you want to figure out what is the minimum cost per unit. So if you only build one, it's like $40,000 per X-ray machine. But if you build two, it might be only $20,000 per machine. And that cost per machine is going to go down, and it just wants you to find what is the minimum cost. And companies do this sort of calculation all the time. They look at how much things cost, how much they pay people, and how much room you have, how many you can compute, and they decide we need to make 20,000 of these. If we make 30,000, then we're going to lose money because we have to pay overtime or we run out of materials or something like that. All right, 1.1b. Go for it.